Hey everybody. Turns out we're still in section 2.4, and this is one of the most packed sections that you're going to find in terms of the amount of information that you need to be able to handle. The main focus is, can you graph a quadratic function or not? And can you graph it when it's written in standard form, factored form, or turning point form? But along with that, there are a couple of other skills that I'm going to expect you to know and that IB expects you to know. And so I just call those auxiliary goals for this section, and I'm going to make a couple videos, one for each. One of those goals is that you'll rewrite an equation of the form y equals ax squared plus bx plus c in the form y equals x minus h squared plus k, really a times x minus h squared plus k. Can you rewrite a function that's in standard form into turning point form? That's the point there. And then you'll write an equation of a quadratic function given its graph. Hopefully that's pretty self-explanatory as far as what the goal is. Now let's get into this rewriting something that's in standard form and converting it into turning point form. Alright, and you see the directions here. Write the function in the form y equals a times x minus h squared plus k. Alright, so in order to be able to change this equation into turning point form, we've got to be able to figure out a couple of things. We've got to be able to figure out what the values of a, h, and k are. Alright, now the value of a is very easy to find, and the value of h and k, turns out we're going to use completing the square to be able to find out what those values are. Okay, now we learned completing the square earlier in this chapter for solving a quadratic equation, but here's what we're going to do this time. You notice how in turning point form you've got a perfect square following your a? Well, what we're going to try to do is make it so that we have a perfect square trinomial. And let me actually highlight. We're going to turn this specifically into a perfect square trinomial. Okay, so we're going to take the two variable terms, turn them into a perfect square trinomial, and then we're going to rewrite them as a binomial squared. And as soon as we've done that, then the equation is going to end up looking just like what you see right here. Alright, so we're going to complete the square to write an equation in turning point form. Alright, just watch what I do here. The process is actually pretty simple once you've seen it once or twice. Alright, the first step in writing this in turning point form is that we're going to go ahead and group the variable terms together, and we're going to separate them from the constant terms. So we're going to make this x squared minus 9x. Alright, and I left some space inside those parentheses, you're going to notice, because I'm about to add something in there, and then I just left the constant term at the end. Now what I'm going to add inside of here is whatever it would take to make x squared minus 9x into a perfect square trinomial. Now you guys know if you have x squared minus 9x or something similar, as long as that's a 1x squared, the way you determine what to add to this expression to make a perfect square trinomial is you take half of b and you square it, right? Well, half of negative 9 is negative 9 halves, and if I square negative 9 halves, I'm going to get 81 fourths. So watch this. Alright, I'm going to add 81 fourths to that binomial, and that's going to make it a perfect square trinomial. And just to iterate, or just to emphasize what I did, I went ahead and wrote this over here. All I did was take half of b and square it like what you're used to doing. Okay, now I hope that you've thought this through already. What we just accomplished made a perfect square trinomial like we wanted right here, and we'll write it as a binomial squared so that the equation is in the correct form here in a moment. But we've increased the right side of the equation, and the left side of the equation didn't change. So now the right side is bigger than the left side of the equation. Ordinarily, the way you would handle that is you would add this quantity 81 fourths to both sides of the equation. Except that if we're going to write the function with y by itself, then we don't want this to become a y plus 81 over 4. So what we're going to do is we're going to compensate for the fact that we added 81 over 4 to the right side of the equation in a different way. And that way is going to be this. We're going to subtract that same value from the right side of the equation so that in essence you didn't add anything to that side of the equation. So like this. Okay, you can agree, I think, that if I add 81 fourths to the right side and then I subtract 81 fourths still from the right side of the equal sign, that means the value of the right side of the equal sign hasn't changed. It just looks different is all. Okay, now if you've got that down, then you know how to rewrite something in turning point form, because the only thing that remains to do is this. We're going to go ahead and rewrite that perfect square trinomial as x minus 9/2 squared. And then we'll add the 2 with the negative 81/4. That's 8/4 minus 81/4. So minus 73/4. Okay, so there we go. We've got our equation written in turning point form. We can now see that a for this equation is 1, just like it was in standard form, by the way. If a is 1 here, a is always going to be 1 here. And then we can now see that the vertex of the graph of this parabola would be 9/2, comma, negative 73/4. Okay, if you've got that down, try this next one on your own. There will still be other examples I need you to watch me for, though. I'm going to give you a moment to pause this and try it. Watch in a moment and you'll see my work. Super easy, right? So I grouped the x squared and 14x together, completed the square, and then I made sure I subtracted the same value that I added so that I, in essence, didn't change the value of the right side of the equation. And then I just rewrote it in the form x minus h squared plus k, where h would be negative 7, or the vertex, I should say, would be negative 7, comma, negative 39. All right, for this next one, I'm going to change it up a little bit. I'm going to make it where a is not equal to 1. And so there's going to be an added step that you're going to have to follow through with. All right, so watch this one. I'll give you a chance to try 1 or 2 on your own afterwards. Let me start by grouping the x squared and the x term just like we did in the previous 2 examples. Nothing different so far, but here's where things are going to change. Remember that if you're trying to create a perfect square trinomial, that you have to have your a be equal to 1. We need this to be a 1x squared, not a 6x squared. Okay, so we need that to be the same here in order for half of b squared to do what we want it to do. However, we're not just going to divide everything by 6 in this case, all right? Because if we divide the right side of the equation by 6, then we have to divide the left side of the equation by 6. And then the left side of the equation is not y, it's y over 6. We don't want that. So the way we're going to handle that is, instead of dividing everything by 6, what we're going to do is we're going to factor the 6 out of our variable terms. And so that'll look like this. Simply, you'll have y is equal to 6 times x squared minus 5x. All right, then I'll still leave the room for adding something in there, minus 17. And now I can go ahead and follow through with our process for making a perfect square trinomial. I can take half of negative 5, which is negative 5/2, and then square it. And that's going to be 25/4. Okay, so that part should make a lot of sense. Now here's one more thing that we've got to pay attention to. Think about if I were to distribute this 6 right now. I wouldn't get 25/4 if I can't say that I added 25/4 to both sides of the equation, because instead I added 6 times 25/4. All right? So it's a little bit more difficult to determine what I actually added to this side of the equation. Well, at least it's not just this number right here. Since what I really did was add 6 times 25/4, what I'm then going to do is I'm going to subtract. Whoops. There's a pen for that. I'm going to subtract 6 times 25/4 from the end. All right? So that way, the same value that I added to the right side of the equation is going to get subtracted from the right side of the equation. And so nothing has been gained or lost. The right side of the equation is exactly the same value as it started with. It just looks different. All right, so from there, we're going to end up with this. We'll have y equals 6 times x minus 5 halves squared minus 17, and then negative 6 times 25 fourths, negative 150 over 4. That's negative 75 over 2. Alright, and then we'll combine our constant terms there. Negative 17 is negative 34 halves, and negative 34 halves minus 75 halves would be negative 109 over 2. Alright, the numbers didn't work out so nicely, the fractions and all, but if you understood what I did with the A that impacted this problem, then you're ready to try one of these on your own. If not, I've got one more example that I'll do for you, and then you can try the last example on your own. Alright, let's go to the next part. That didn't do exactly what I wanted to. Hold on. There we go. So we're going to write this in turning point form. You're going to have to remember to factor out this 0.25 from the variable terms whenever you do it. If you're ready to try it on your own, go ahead. If not, watch me in this example, then try the last one on your own. No matter your skill level, you ought to have been able to get here on your own. We grouped the variable terms together, and since I need that to be a 1x squared right there, I factored out 0.25 from both terms. Although I've kind of left out what this factor is, just because I want to make sure you understand it. Alright, 0.25 factored out of 0.25x squared is going to leave me with x squared, obviously. What do I get when I factor 0.25 out of 2? Well, what would you multiply by 1/4 essentially? That would give you 2. Well, that would be 8. So you should have a plus 8x right there. And as soon as you've got that, then you can go ahead and make a perfect square trinomial. Take half of 8, you get 4. Square that, you get 16. Alright, and then make sure you know that what you've actually increased the right side of the equation by is not 16, but it's 0.25 times 16. Alright, you've got to have the vision to see that if you were to multiply that 0.25 by each of these terms, it's not 16 that you increase this by. Okay, so 0.25 times 16 is 4, so we're going to subtract the 4 that we added already. And so you'll get this in the end. Alright, y is equal to 0.25 times x plus 4 squared minus 10. Alright, this last one you're going to need to try on your own. Alright, so here we go. I did the first couple of steps kind of together there. I took the negative 3x squared minus 12x and factored negative 3 out of them, grouped them together. Alright, so negative 3 factored out of the first two terms gave me x squared plus 4x. And then I just left the 5 at the end. And then I took half of 4 and squared it, which was 4. And I took into account that really what I've done is I haven't added 4 to both sides. I've added negative 3 times 4. Or really then subtracted 12 from both sides, because negative 3 times 4 is negative 12. And so to counteract that negative 12 that I modified this side of the equation by, I also added 12 to the same side of the equation to cancel that effect out. And then I was able to write it in the turning point form. I can tell that my a is negative 3. I can see that the vertex of this parabola would be negative 2, 17. There's how you change a standard form quadratic function into a turning point form quadratic function. Well done. We'll see you with the next video.